All right, so we're asked now the question here to kind of build up a convergence idea. Under what circumstances, in other words, what values of P would this thing end up converging? Now, we've actually looked at one instance where we know that it diverges. So we actually looked at this series a little earlier. Right? We talked about it when P is equal to 1. And we discovered that thing diverges. It takes a really long time, but it's still going to go to infinity. So that thing diverged. That thing diverged. So we know that when P equals 1, this is going to diverge. Okay? That much we know for sure. That case where P is equal to 1, it is going to diverge. Okay, so we know that much. But what about other values of P? So to work this out, we start by setting up our integral test. So integral from 2 to infinity of 1 over x, ln of x to the p, dx. All right, we would use the substitution here. U equals ln of x, du equals 1 over x dx. All right, so rewriting this, we would have limit as b goes to infinity of the integral from 2 to b. And here's what we would have. Rewriting this would be ln of x to the minus p power times 1 over x dx. So let's get a few values out of the way right away. If p starts out as being negative, then we're going to have the integral of ln of x to a positive power. Okay, ln of x to a positive power, even if it's like ln of x to the 0.1 power. Right? And then using our power rule, we would add 1 to the exponent, and we'd keep going. That'd be like ln for 0.1. That would be ln to the 1.1, and as you go to infinity, ln is going to go to infinity, ln to the 1.1 is going to go to infinity. Right? So if p is less than 0 in this formula here, this whole thing is going to diverge. Absolutely no question about it, diverge. If p is equal to 0, then this would just be the integral of 1 over x. And then that means we already know that one diverges because that would be the harmonic series if p is equal to 0. And we know that that diverges. Okay. So now, there's 2 remaining scenarios that we need to consider for p being positive. And that is, first, if p right, is between 0 and 1, then when we do the integral here, we would add 1 to the exponent. So that would mean minus p plus 1 would be greater than 0. Minus p plus 1 is greater than 0. And so when you do the integral, minus p plus 1 will be greater than 0, we're going to have ln of x raised to some power. As ln goes to infinity, ln of x to that some power is also going to go to infinity. So this situation is also going to diverge. Right, we're also going to diverge there. I guess I can leave off yes because it's plural, and I should have left off yes there as well. Okay. Then there's the situation of p equals 1. We already know that diverges because we did it above. All right, so see above, we did that example earlier. So that brings us to the final scenario. What if p is greater than 1? If p is greater than 1. Well, then minus p plus 1, when p is greater than 1, minus p plus 1 is less than 0. Is less than 0. So that means when we apply our power rule here, right, this will be the limit as b goes to infinity of ln of x to the minus p plus 1 divided by p plus 1. All right, that's all evaluated between 2 and b. And so when p is greater than 1, minus p plus 1 will be greater than 0. So that means we drop the negative sign and move it to the bottom. So we would have limit as b goes to infinity, 1 over, that should have been a minus p plus 1 there, 1 over minus p plus 1 times 1 over ln of x to the p minus 1. All right, when we factor out the negative there, and that's evaluated between 2 and b, this thing is going to converge. All right, this thing is going to converge to whatever minus 1 over p plus 1 ln of x, well, the integral will, ln of x, ln of 2 to the p minus 1 power, whatever the heck that is. But that stuff with the b, as b goes to infinity, all of that's going to go to 0, right? Because you're going to have 1 over infinity. So it will therefore converge. So it turns out the one we looked at earlier, if that had had just a slightly bigger exponent on it than 1, it would converge. Okay, so we've kind of reached that dividing wall there. And the same thing happens with p-series. Same thing happens with p-series that we already talked about as well, right? P equals 1 is that dividing wall. That harmonic series is that dividing wall. If you get bigger power than 1, then you're going to converge, right? But if you're 1 or smaller, it's going to diverge. And it actually turns out this series that we set up here with 1 over k ln of k to the p actually has that same kind of rule, that if it's p is greater than 1, then the series will converge. So to kind of summarize what we had here, the sum of 1 over k ln of k to the p converges when p is greater than 1.